The following video covers Part 1 of the Unit 9 review dealing with the gas laws, Boyle's, Charles, Gay-Lussac's, the combined gas law, and the ideal gas law. The four measurable properties of a gas include pressure, temperature, volume, and the number of moles present. Pressure is just a measurement of the force per unit of area. When you're speaking of pressure of a gas, pressure is caused by gas particles colliding with one another and also with the walls of their container. There are many different units that pressure can be used or can be measured in. Some of these include atmospheres, pascals or kilopascals, millimeters of mercury, inches of mercury, pounds per square inch. There's another one called torr. Torr is the same thing as a millimeter of mercury. All of these are common pressure units. To convert temperatures given in degrees Celsius to Kelvin, it's very simple. Because there is a direct proportion, all you have to do is take the Celsius temperature and add 273 to it, and that will give you your temp in Kelvin. And the important thing to recall is that the reason why the Kelvin scale is used, it has no negative values. There is a lower limit of temperature, which is known as absolute zero, which is 0 Kelvin, which corresponds to negative 273 Celsius. Because temperature is really the average kinetic energy of particles, so basically how much the particles are moving, you can't have less temperature or less movement than no movement. And so that's this idea of absolute zero. The reason why we have to use Kelvin in the gas laws, if you use Celsius temperatures, it leads you to scenarios that are impossible, where you will calculate like volumes of gases, and if there's a negative temperature, you end up with negative volume. Negative volume is nonsensical. You either have volume or you don't. Boyle's law is the relationship between pressure and volume in gases. Pressure and volume exhibit an inverse relationship. Inverse means as one goes up, the other goes down. So, for example, pressure and volume. Think of having like a balloon in your hands. You take that balloon and you add external pressure to it. What's going to happen to the volume? It's going to smash down. Why? Largely because gases are compressible. The particles are far apart. Conversely, if I release that pressure, the balloon is going to expand back out. So as the pressure goes down, volume goes back up. Charles' law is the mathematical relationship between volume and temperature of gases. You will notice that volume and temperature are directly proportional. That means as one gets larger, the other does as well, and vice versa. As temperature goes down, so does the volume. Think back to an example with the balloon plunged in liquid nitrogen. As the temperature of the gas inside the balloon decreased, the volume decreased and it shrunk down. When it was sat out on the counter, the temperature rose and therefore the volume increased. The combined gas law is really just a combination of Boyle's, Charles, and Gay-Lussac's that we didn't have on this packet, but you will notice that it is the relationship between pressure, volume, and temperature of gases. Anytime you have a gas law problem that includes the number of moles, you will need to use the ideal gas law, simply stated PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is something called the ideal gas constant. And you will notice over here we have three different values. There are some other ones, but these are three common ones for different values for the ideal gas constant. You will notice that the only thing that they vary on is their unit of pressure. So if the pressure is given in atmospheres, you use 0.082. If you have kilopascals, you use 8.31. If your pressure is in millimeters of mercury, you use 62.4. And then finally your temp, and once again, temp always has to be in Kelvin. As long as volume is held constant, the pressure of a gas will increase as temperature increases. Why this is because the particles, as temperature increases, they have more kinetic energy. They're moving around more rapidly. Therefore, they collide with each other in the walls of their container more frequently. The additional collisions cause added pressure. Okay, if you have a gas and you compress it, you put it into a smaller volume, it wants to know what happens to the pressure. Well, the particles, since they're going to be closer together, they're going to have more opportunities to collide with each other and with the walls of the container which they're contained in. Therefore, as volume goes down, pressure goes up. The three parts of the kinetic molecular theory that apply to gases deal with the fact that particles of a gas are considered to be small hard spheres with insignificant volume. That means they're really spread far apart, which means you're able to compress them. The second part is that the motion of the particles is rapid, constant, and totally random. They tend to travel in straight lines until they strike some object, and then they'll move off in some new direction. And then the third portion states that the collision between the particles in a gas are perfectly elastic. The opposite of an elastic collision is a static collision. If you have a static collision, the particles, when they collide, they tend to stick together. Elastic sounds just like, well, it is. You think of like elastic, like the elastic band in underwear or something where it's stretchy or bouncy. While as gas particles collide into one another, they bounce off and head in new directions. The kinetic energy is conserved. If they're both traveling at the same speed initially, they don't speed up, they don't slow down, they just move off in new directions. Whereas if you have gas particles traveling at different speeds, the one that's moving faster will impart some of its speed to the one moving slower, and they will move off in other directions. But once again, kinetic energy is conserved. What happens to the volume of a balloon if it's left in a car on a hot summer day? Well, as you know, cars in the summer get hot. Why? The sun's energy goes down through the glass, warms the interior of the car. The heat energy isn't able to escape. So therefore, the temperature, the interior temperature of the car increases. As temperature increases, volume will also increase. As those particles are moving around more rapidly, they're taking up more space, volume gets bigger. Gases are more easily compressed than solids and liquids, largely because the particles in a gas are spread far apart, whereas particles in a solid or a liquid are generally packed in there fairly dense, about as dense as they can be. But gases, lots of space between them, they can be compressed. And here's our old friend Avogadro. Avogadro's principle basically as how it relates to gas. It states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. Avogadro, we recall, or we have honored him with Avogadro's number, that number that represents a mole, 6.02 times 10 to the 23rd. Avogadro had really no concept of what the mole was or how large the number representing a mole of anything is. But where he come up with this idea was the fact that if I have two volumes of gases, same temperature, same pressure, they have the exact same number of molecules, independent upon which gas they are. It doesn't matter if they're very large molecules or very small one. It doesn't matter if it's hydrogen, helium, or sulfur hexafluoride, or radon gas, any of those. It'll have the exact same number of particles.